Hi, my name is Mike Smithson, and the title of my talk is Flexible CDF Quantile Distributions on the Closed Unit Interval. For a long time, modeling doubly bounded random variables has been hampered by the fact that most useful distributions have support only on the open unit interval, or support on the closed unit interval, or the compact interval, only conditionally. And this is a problem for maximum likelihood estimation, for instance. Four approaches to this problem have been widely used. First, we can replace the zeros and ones with values nearby. So in other words, we shrink the scale away from the boundaries. Second, we can use hurdle models, which I'll describe shortly. Third, we can use truncated or censored distributions. And then finally, we can use available distributions with support on the compact unit interval. It might be tempting to think that we could get away with just shrinking the scale. And so I've got an example here where I've successfully fitted a beta distribution to this U-shaped distribution by shifting the zeros and ones very slightly away from the boundaries. The problem is that if I shift it differently, if I shift it a bit more away from the boundaries, then I get quite different results. And so the problem is, what's the correct shift? What about hurdle models? Well, these combine logistic regression for modeling the zeros and ones separately from modeling the data on the open unit interval. These are so-called boundary-inflated models, like a boundary-inflated beta regression. But if the data are regarded as being generated by a single process, then these separate models are a bit incongruous, because here we're treating the zeros and ones as if they're qualitatively different from the data inside the unit interval. Truncated and censored distributions lack sufficient shape flexibility quite often. Truncated distributions, for example, can't have modes at 0 and 1, while also having a mode in the interior of the unit interval. And censored distributions always have a discontinuous jump in the densities at 0 and at 1. And they also don't treat zeros and ones as true scores. Well, what about the distributions that are available that have support on the compact interval? These have important limitations too. Some of them simply lack sufficient shape flexibility. Others have restricted densities at 0 and at 1, so they're not flexible enough about the densities, the limiting densities. One of the most flexible approaches is fitting splines, or distribution functions, to quantile data. But these use a restricted number of quantiles for estimating these things, typically 3 or 4 of them. And so it's not sensitive to all parts of the data, particularly the ones that are not captured by those particular quantiles. Now, a subfamily of the CDF quantile distributions that Ian Shou and I came up with actually does have support on the compact interval, and they can have both an interior mode and modes at 0 and at 1. But they're limited by the fact that the densities at 0 and 1 always are equal to each other, so their applicability is very limited because of that. Nonetheless, we can try taking these distributions and see if we can improve them. Here's the original CDF quantile distribution function. So we're taking a CDF function, f, which is a standard function for a variable that has support on the real line, and we're applying it to another quantile function for a variable that also has support on the real line. And then we're transforming that with 2 parameters. One's a location parameter, mu, and the other is a dispersion parameter, sigma. A function with a third parameter that can augment these distributions could be put in any of these 4 places. 2 of these places involve a function which I'm going to call v that maps the compact unit interval to the compact unit interval. And so we can have either an inner position for v, where it's transforming the variable directly, or an outer position where it's transforming the CDF f. We can also transform the function with a function called w that maps the real line to the real line. And again, we have an inner position for w, and we have an outer position for w. The w function that works is based on a skew transformation published by Jones and Pusey. What I've done is to knock out one of their parameters and just retain one of them, theta, which controls skew. It turns out that this function has a derivative with limits e to the theta as y goes to negative infinity and e to the minus theta as y goes to positive infinity. So this would seem to be the kind of function we want to have. A v function that works and has a similar result is sometimes known as a tilt parameter function because it also controls skew. And this function also has a derivative with limits e to the theta as x goes to 0 and e to the negative theta as x goes to 1. Given that the original CDF quantile distributions limiting densities are a function of the dispersion parameter sigma, then the chain rule implies that this new density limits are simply going to be rescaled, rescaling the function for sigma by e to the theta as x goes to 0 and e to the negative theta as x goes to 1. So this would seem to be the kind of augmentation that we want to have. Let's see how these work. Theta controls skew, as I mentioned before, and it partly controls the densities, the limiting densities at 0 and at 1. So the examples that I have here have fixed mu and fixed sigma and varying theta. And you can see that theta is influencing not only the densities at 0 and 1, but it's also influencing location because skew and location are correlated with each other when you have doubly bounded random variables like this. Mu, on the other hand, controls location, but it doesn't influence the densities at 0 and at 1. So the distributions I have here have varying mu and fixed theta and fixed sigma, and you can see that that's exactly what's going on. The densities at 0 and 1 stay the same, but we've got location shifting around. Finally, sigma controls dispersion, and it also partly controls the densities at 0 and 1, as I indicated before. And what it does is to either inflate or deflate both tails. So it inflates or deflates the densities at 0 and also at 1. Now, I'll give an example of an application. What I'm going to be talking about is modeling the proportion of patients' time spent in an emergency department at a Canadian hospital in two stages. First, the preliminary registration and triage stage. Now, one of the main predictors of proportion of patient time spent in this preliminary stage is whether they arrived by ambulance or are a walk-in. So we're going to use this binary variable as a predictor here. And the hypothesis is that the ambulance arrivals spend a smaller amount of time in the preliminary stage because they oftentimes have life-threatening disorders or injuries, more serious injuries than those who are walk-ins. And so this is going to affect theta. And we'll use a two-parameter interposition tilt parameter arc, hyperbolic arcsine distribution to demonstrate this, to illustrate this. In two submodels, theta has a term for x, the binary ambulance versus walk-in variable, and sigma, we're just going to have an intercept model for it. It turns out that the effect for x is significant on theta, and it's in the expected direction, and the fitted distributions in the graphs here show that they're matching the data pretty well. The hypothesis has been supported. If we now look at the opposite effect for how long people spend in the treatment stage, we get a similar story. Ambulance arrivals spend longer there than walk-ins, as we would expect. And again, we can see that the fitted distributions are doing a good job of matching the data. And again, both of these cases, the zeros and the ones are zeros and ones. Okay, so the new distributions can handle zeros and ones. They're continuous, and they have some promising properties. Both of them have flexible distribution shapes. They can have an interior mode, and they can also have modes at 0 and at 1. They can model location, dispersion, and skew. And like the original CDF quantile distributions, these new distributions capture all of the quantiles with only 2 or 3 parameters. What I can't show here is I've done a lot of simulation work to demonstrate that they have accurate and nearly unbiased maximum likelihood estimates. And likewise, they also have reasonably accurate type 1 error rates. Are there any caveats? Well, yes, there are. They need to be used with some care because, first of all, parameter estimate collinearity can be a concern here. This is something that comes up with doubly bounded random variables anyhow. Because skew, location, and dispersion are they're not independent when you have doubly bounded random variables. It turns out that the outer position distributions suffer less than the inner position ones from this, and so the outer position distributions are more likely to be successfully fitted to data, especially the 3-parameter ones. There's still a lot of work to be done on model evaluation, developing appropriate residuals for models using these distributions, and interpretive effect size indicators. But nonetheless, we're optimistic about this new distribution family. We think it has a lot of potential for applications. And thanks for listening.